I did turn it in.
He turned it in, but it's wrong. And so then he asked a question. He wanted to make sure he got it in. Okay. Couple of things. I haven't heard back again if they'll do 2 beams, but I'll let you know as soon as that is, because you might. And I don't know. I can't do the selecting teams. I just feel too bad. I feel too bad because someone's. If you all agree to it, then we could do it that way. Okay. But we're gonna see if we can have 2 teams though first. Okay.
I think we should pick them now so
And then.
we know where people stand.
Yeah. And then another announcement is I'm teaching masonry next semester. And what's the laughter? You sons of bitches. I've never taken masonry. I don't know anything about it, so we'll be learning it together. Yeah.
Welcome to It's Gonna Be Learning.
Here we go. That's right. You get that experience again. So.
How do you guys actually do
That's what it is. So when I told, because we couldn't find anybody else to do it, so I'm not going to teach the coding. We're not going to do that one.
Oh.
I know, yeah.
One time.
Yeah, because I need to teach masonry instead. And we tried to get, I tried really hard. We had an older student, Morley was going to do it, and then. Oh, and Morley and Austin were going to do it, and then we showed them what notes they have to work with, and they're like, I don't know. And then they have travel and stuff, and they were like, they panicked a little bit. Chris Van Lucian did it for us years ago, but you guys and he was able to do it because Morley was there to fall back on. But then now, if Morley leaves, he has nobody to fall back on in that group, and so he's like not going to do it. So quit being so disappointed. I'm fucking doing it, Kira. Okay, I'm gonna nail it. All right. Yeah. Basically, Morley wanted to use Austin as a grader. It's because we're like, maybe the 2 of you could do this, and Morley's like, no. Like, I'll do it, and then Austin would do the grading. Yeah, Austin was fine with it, but they did not. Nobody wants that, and so he's fine. He just didn't put the effort into doing it right, and so. I'll put lots of effort into it. And then Timothy was just like, oh, well, there goes my semester. You're going to be dealing with you a lot. And so Tim will be teaching it to me, and then I will then relay it to you guys as we go along. I will say about half of it, it's the class is mislabeled a little bit. It says masonry design, but half of the class is just advanced structural analysis stuff, right? We're going to dive deeper into the seismic code, deeper into the wind code, deeper into we talk about diaphragm design and work our way out. And then we'll do a little bit of masonry at the end. So I think we've always been talking, and that's how it's always been taught before. It usually has pretty good reviews because it does kind of put it all together. It's like a more advanced structures 1 where we revisit that. And Tim said he learned it this way back in the day. He said it was great. So I can handle the first half. It's just the second half I'll be teaching. Like, honestly, I don't know what code you use for masonry design. I don't even know that. Do you know what code to use for masonry design?
Isn't there like a book?
Yeah.
There is a specific.
Yeah, it's like ACI but for masonry.
But everyone at Morrison Maryland was like, I was asking like, does anyone know how to do this by hand? And everyone was like, no, just throw it into this program.
Yeah, Intercalc, yeah.
And I was like,
That's the
okay.
only experience I have.
You throw it into Intercalc, yeah. So, there you go. We don't need to do it. So, I'll show you how to use the
VA has a module that's totally just
for masonry. So maybe we'll focus a lot on that. We'll see. Right? I mean, for reals, right? Make sure we know how to enter it and they're fine. Okay. So what we were in the middle of talking about was ultimate capacity. I assigned a homework on calculating the ultimate capacity. Right? This is it. These are the mechanics that are going on. We've spent quite a bit of time on this. It's just like regular reinforced concrete, but what to use for this FPS. Your homework, you have it where you use FPS equal to Fy, and you do it where FPS is equal to the ACI empirical equation. Just doing it those 2 ways. And so you'll set it equal to that. You'll set C equal to T. It'll tell you where the neutral axis depth is. You then sum the moments about one of the points, and then that'll give you MN. And then you have to calculate phi. Phi is going to be based off of that A that you were given, or that you solved for, that neutral axis depth. It's going to be based on what epsilon is. Where is it at? Right here, right? So then once you find the new triangle, you calculate MN by sum of the moments. You come back to this triangle right here. You do similar triangles. You solve for the neutral axis depth, and then you solve for what epsilon to PU is for that. And then that'll tell you what that strain is. You compare that to 0.005 or less, right down to 0.002, and then there's a little equation for what it is in between there. That'll tell you what your phi factor is, right? I think your homework, they're really close to being compression controlled. They're really close to being either they're 0.65 or they're like 0.66 is what you should get for your phi factor. Right? It is, and again, that's typically not allowed in regular reinforced concrete, but when you have pre-stressing, it is allowed to have compression controlled failures. Right? In regular reinforced concrete, remember that strain has to be greater than 0.005, and that does not apply to when you have pre-stressing. Okay, the next topic is minimum reinforcement. Okay, just like regular reinforced concrete, there's a minimum amount of reinforcement you have to include. Right, and it's tied to this cracking moment. Remember, I'm not texting. I'm just sometimes I text, but not this time. Okay, so this is what it says right here. For beams with bonded pre-stressing, total quantity of AS and APS, AS is just a regular steel and APS is your pre-stressing, shall be adequate to develop a factored load at least 1.2 times the cracking load calculated based off of FR. Okay, so then what does that mean? Right, so usually this has to happen, right? This absolutely has to happen. You have to make sure that phi MN has to be greater than or equal to MU, right? That's the first thing, right? You have to make sure your calculated demand is greater than, your calculated capacity is greater than your demand, right? But the other thing, what this statement over on the side says, it says that phi MN has to be greater than or equal to 1.2 times M cracking. Okay? That's an additional requirement. This is just to make sure people don't die, right? Capacity has to be greater than demand. But in this case, it also says that our phi MN has to be greater than 1.2 times the cracking moments. Cracking moment isn't a demand, it's another capacity, right? And so what this is tied to, anybody remember what the minimum reinforcement is tied to in regular reinforced concrete? Neil?
You were talking.
Yeah, Kira. The minimum reinforcement in concrete. There's a minimum reinforcement requirement, right? It's like, no, I don't really care what it is, but why? Why do we have why does this have to happen? Why does my phi MN have to be greater than 1.2 times the cracking load? It's to avoid a brittle failure, right? And so what happens is, it starts out with mechanics, right? It starts out with mechanics like this, right? Where you have, a stress distribution like this, right? It starts out linear like this, right? And then it switches, right? When the failure mechanism, it switches over to this. Right? When you calculate the ultimate capacity, it goes from this to this. So everything's linear, right? Everything's linear, everything's great. Then it cracks, and then it goes out to this ultimate moment capacity. The mechanics switch from this to this, right? If this capacity, right, these mechanics over here where everything's elastic, if this capacity is greater than this capacity, then what happens? Fails brittly, right? It goes like this. It goes, oh, everything's great, cracks, switches to this mechanics, oh shit, this capacity is smaller than this capacity, fails instantly, right? Gone. Typically, we try to avoid that, right? We avoid, first of all, we don't want to get to a point, this is ultimately what handles it, right? That this phi MN has to be greater than MU. But what if MU got too big? And MU got so big that it actually cracked the beam, and it went from this type of mechanics to this type of mechanics, and this capacity is smaller than this capacity, it would just fail. And then we don't want that. We don't want people to first of all, we don't want this to happen, but if this happens, we want it to fail in such a way that we see failure and we get out of there, okay? So I don't know how to write that. I don't know how to write that. No, yeah, you're okay. Let's see if this. Okay, it works now. I had to fix that. Let me go back to this. That's when it goes backwards. I got it. Okay, I got it. That's what it tries to do. Mirror presenter page. Now if I just mirror the presenter page, then I think it works. Maybe it doesn't. God, now I can see it. God damn it. God damn, I thought I fixed it. Remember I fixed it. It worked for a second.
It worked when you were in the other view. Yeah, it didn't work when you're in full
Have you
screen.
heard of Hive Mind? No, I've never heard of Hive Mind either.
God damn it.
It was working.
It was working and I fucked with the deal. God damn it.
Let's put a mirror on the back wall.
Put it here. Oh, now it's just, now I can't even, now I don't see that anymore.
This is what you get for updating the way we want.
That's what I get for, ah!
Why do you say
Perfect explanation.
I can't even see that. God damn it. God damn it. Yeah, Masonry's gonna be great. Masonry's gonna be great, guys. Okay, I got it. That was just really large. All right. Aha.
actual
Word, yeah. If cracking moment exceeds ultimate moment, you will get a brittle failure. Ah, you get a brittle failure. Right. Mechanics change from elastic to Whitney stress block stuff, right? I mean, that's right. Right. Right, that's it. You get it. I was just trying. How else can I write that? I mean, that's it. That's it. You get it. Do you get it? All right. It goes from this. Goes from this over to this, right? It goes from that mechanics to that mechanics and get a failure. So that's where the requirement. So technically, you'll run into the problem, right? When it's phi n has to be greater than the cracking moment. But this 1.2 is just a factor safety. Like you can't just be right at it. You actually have to go 20% higher than it. Matthew, you're sitting in a different spot today, and you're really throwing me off. You're really throwing me off. It's like, who's that kid? Where's Matthew? Who's this kid over here? Okay. All right. So then here's the deal, right? How do I calculate the cracking moment? Right? Well, this is how I calculate the cracking moment. Right? My equation for stresses, right? My equation for stresses is negative FPE all over AC minus FPE EP all over S1 plus, we'll call that M cracking all over S1, right? And that's equal to the rupture strength. So it's, right, we're talking about the mechanics that we're dealing with right now, right? Which is everything's elastic. So this is our equation for calculating the stress. And what we're talking about, we're worried about under normal conditions, we're worried about cracking at the bottom, which is 1, right? And so I just take, that's my normal stress equation right there for calculating what F1 is. And I'm trying to find this thing right when it cracks. When it cracks is when I hit my rupture strength of my concrete. So this would be equal to 7.5 times the square root of F prime C. So that's a known. We know what this left-hand side is. This is 7.5 squared F prime C is my rupture strength of my concrete, right? When my moment, and this is my unknown right here, is this MCR. That's what I'm after right here. If I apply a moment greater than, right, you'll calculate, I mean, so you got to do a little algebra. There it is. You're just going to solve for this MCR over here, right? Rearrange this equation, solve for MCR. If my moment is bigger than MCR, it'll crack. If my moment is less than MCR, it won't, right? And so where does this 7.5 squared F prime C come from? That comes from over here on the right. It says, right, for beams with bonded pre-stressing quantity AS, it shall be adequate to develop a factored load at least 1.2 times the cracking load on basis of FR defined in 19.2.3. If you go 19.2.3, this is where we got that 7.5 squared F prime C. Right, there's a lambda in there. That lambda is associated with lightweight concrete. Right, so if you have lightweight aggregates, then you modify that 7.5 squared F prime C. If you're using regular weight concrete, it's just 7.5 squared F prime C. So that's where you get M cracking from, is from our thing. So that's what you'll do. So in your homework, you have to do this, right? And so say what happens, you go through and you violate this, right? You go through and you find out that phi mn is not greater than 1.2 times M cracking, right? So what can you do? It was the minimum reinforcement requirement. So you could add more reinforcement, right? So say, okay, instead of 8 bars, let me use, or 8 strands, let me use 9 strands. But what's the problem with doing that? If I go from 8 strands to 9 strands, what else goes up? The cracking moment. My cracking moment also goes up, right? So if I just say, oh, I need, because FPE, right? FPE has the number of strands in it. So if I add more bars, then my cracking moment goes up, which means that end up chasing your tail if you start doing it. If you keep adding pre-stressing reinforcement, you're increasing your cracking moment at the same time you're increasing your phi mn, and so you've run into some problems. So what do you think you could do? Add in normal reinforcement, right? You add in normal reinforcement will not affect your cracking moment, but it will affect your phi mn, right? So by adding normal reinforcement, this will go up, and then M cracking will stay the same, okay? If I could say that in words. With typing. Ooh, yeah, there we go. If you violate this requirement, you should add regular rebar. This will increase MN, but not MCR. MCR. If you add pre-stressing, increases MCR and MN, chasing your tail. Chastising tail. Look at that. Okay, there's a little philosophical in here today. Does that make sense to everybody? Kyle, you got that? Neil, you got it? That was cool listening to Kinsey last week. I thought it was neat. Career path for you. You want? Billings. There's a way out. There's a way out, Neil. I read that meth story. Yeah, it's pretty funny. I guess they've been doing it for years. They've been doing it for years, and then I guess the pet place didn't know that they were doing it. Yeah, but they didn't know what they were burning in there. They didn't know they were burning meth in there. And then, so something happened where the flume got plugged, and so then it went down, and then it just it backed into the and all the workers were in there, and they had to evacuate all the animals because they had some animals in their stuff in there, and then Billings.
Or they knew when the workers plugged it up
So they could smoke meth. So they could smoke meth. Okay. Does that make sense to everybody? It's kind of neat. Little academic exercise, right? What I should have done in the homework is I should have added a layer of non-pre-stress reinforcement. Just make it a little harder, but I didn't. And so, yeah, I will do that. Because then what ends up happening is you would have an FPS and a T from the pre-stressing, and then you would have an FY and a T from the regular reinforcing steel. You'd have both of those. So in your equations, right, in your free body diagram, you'd have since it's an I, you're going to have a compression in the web and a compression in the flange, two of those things, and then you'll have down below you'd have two T's coming out, one from the regular reinforcement and one for the pre-stressing. Okay. For post-tension unbonded, the mechanics are different, right? You don't get that same brittle failure because you don't have the steel isn't bonded to it, and their stress distribution is spread out, and it's not as tight as that. So they just come in and for pre-stressed post-tension stuff, you use this. It just has a limit for it. They just come in and just tell you exactly what the limit is. No Phi-Mn greater than 1.2 MCR. It's just an empirical relationship. You just put it at that value. Okay. So let's talk shear strength, right? That's ultimate moment capacity. This has to happen too. We have to make sure that Phi... Any questions about moment capacity? So now you got everything for your homework. You can do all your homework right there. You have to do that cracking moment. You have to check that. You have to make some statements in there, something like that. Okay. So now we're in the shear capacity. Your next homework. Phi Vn has to be greater than or equal to Vu. Right? This is a life and death thing as well. So there is a Phi. There's a Phi factor. We'll pretend our capacity is less than it actually is. And then Vu will pretend our loads are actually bigger than they are. So we have to meet this requirement as well. Okay. Potential for shear concern in the following members and scenarios. So typically it's not going to be a problem, right? No, I guess it's right there. Well, it keeps changing the size of this. Typically pre-stressed beams are long and slender. Shear unlikely to control, right? Because one of the reasons we're doing this is to get longer spans out of everything, right? And since they're just very flexible members, right? And because of that, it's typically not a problem. However, web is often thin and carries much of the shear load. Right. Shear stress is high in slender webs. We'll look at some of that. I'll refresh your memory on some of these things. You know, oftentimes our members are going to be kind of I-shaped members because they could do that, especially pre-stressing because they make those things at factories, right? So they can make it, they call them bulb tees, right? Or they have inverse T. They have a bunch of shapes that they use. So they're usually like some sort of I shape. And if you remember what the stress distribution, this is back to mechanics and materials, right? It's something like this, right? Do you remember seeing this at some point? Yeah, on Friday? Oh, you did cover up Friday? Oh, in solids, yeah. Tau is equal to VQ over IT. Right? That's the equation for that stress, right? right? And then what changes between the web and the flange is the T, right? The Q actually changes between the web and the flange too, right? Is it Q? No?
Yes.
Oh, it does. Okay,
Very
Q
good.
changes.
Very
Oh, yeah,
good.
you're right.
Very
Yeah,
good.
yeah,
Very
yeah.
good.
Yeah, but you're right. So, but there's a big, right? So just to show you, right? The web is where you're gonna have some problems. They're very, very thin web. So we're gonna look a little bit later and see like where at on the beam this is gonna be a problem, right? But obviously, the web is gonna be part of the problem, right? And then also can also be an issue. I just learned this word a few years ago. Adapt ends. That sounds kind of cool. Adapt to end. It's this. You guys, have you run across this in class or anything? Adapt end. It's like when you have an I-beam coming across, or like some sort of, and then the top keeps going to here. I'll draw it like this. Probably should use different colors here. Right? Does that make sense what's happening here? Right, so you got this, like maybe this is a T-beam I got coming across. The T-beam spanning across, and then you stop the web here, and then you just let the flange keep going, and then that's what it's bearing on. Right? And you can see that you could have some problems with shear there, right? Because your depth is very short. Now, instead of having the full length right here, you've just transferred it all just to the flange that gets carried over. It's called adapt end. Learned something today, DL. Yeah, I learned that a couple years ago. I'm excited about it. You haven't run into that yet? Real world people? Adapt end?
With wood. With timber, yeah.
You did? Do they call it adapt ends?
I just call it notch.
Notched, okay, yeah. Dapped or notched. Dapped sounds cooler, by the way.
Thing you're not supposed to do with wood.
Yeah. You can do it, but you're not supposed to do it.
1/3 of the depth is the limit.
So then that's the beams you have to worry about that. Okay, where you have to worry about it in slabs. It's my favorite kind of failure mechanism. It's the scary one. Punching shear. An issue because PT slabs are hella thin. That's what I had written in my notes. I don't know why I said that last time, but it's pretty funny. Punching shear can be an issue because PT slabs are hella thin. Right? That's one of the reasons why we do PT slabs, is so that we can get away with a lot smaller slab heights. Okay? And because you have such smaller slab heights, then you can have a punching shear problem, right? So if you have Cobley is a flat plate, right? So there's a big flat plate, and then there's just columns that like extend through the flat plate, and then that's it, right? And that one's scary. And so then what can happen if you put too much load on it, is and the columns punch through the floor, right? That's scary. That's a scary one, right? You don't think punching shear is scary?
No, not ideal.
You don't think it's scary? It is scary, right? It is scary, right? You just think of like, they just say it happened on the top floor, like they put too much equipment on the top floor of Cobley over here. That punches through and then just squishes everybody on the next floor. Now you've doubled the load on the next floor, which is going to punch through, squish everybody all the way through.
I also feel like just the acceleration of that floor coming down would add to that.
Also, the impact load, too. That's right. So my favorite, because it's the scariest. That is what happened in the World Trade Center, right? It was punching. I mean, it was. I forgot about you, Luke. If you believe in that, if you believe that it happened, right? It wasn't an inside job, but it wasn't punching shear necessarily, but it was that, right? There was pancaking of floors going down because you could even see the columns were still sticking up as it was coming down because they were staying put and the floors were punching through. It is. I used to teach a class that we had progressive collapse as one of the topics, and we dove into that. And then I was like trying to find some stuff on YouTube, and my God, there are so many conspiracy theories. And it sounds like, Luke, you may have gotten sucked into that group. You don't really, or you do really think that it's a conspiracy, like it's an inside job.
Yeah.
You son of a bitch. Not for reals.
Yeah.
Oh, yeah. God damn it.
I mean, I'm not 100% sure, but I'm more sure that it's an inside job.
From what? From YouTube?
From the inconsistencies.
What's the inconsistency?
A building shouldn't fall down inward when it's like buildings aren't designed to fall down inward.
But did you see what it was made of? Right? It was like the whole exterior was just like columns, just stacked columns all the way around. It's beautiful, right? And then there's. We're gonna talk at some point. So I was in grad school I was just leaving my Helena, Montana to move to Seattle when it happened, right? It was in September 11th, right? And school started in University of Washington in October. And so it happened right in September, and then I had to go to like a big city. I was fucking terrified. I was so scared, right? I thought for sure. I avoided all like baseball games because the Mariners were playing. They did really well that year, and there was a lot of these big. I was like, I'm not going to any of those things because they were going to get taken out. It was actually a pretty scary time. You talk to your parents about it. You know, they're probably close to my age now, right? But it was scary. When I was at grad school, one of the designers the company is out of Seattle that did like the main structural design. He came and gave a talk to our structural mechanics class and walked us through the whole thing. It wasn't.
You admitted you were wrong?
What's that?
You admitted that like this building.
Well, I mean, the first thing he showed was a cross section of the building, right next to it, a scaled airplane, and it's the same size. And he's like, of course the fucking thing's gonna come down, right? You have this thing filled with fuel, and you fucking ram a building the same size as the plane that hits it. Like, of course it's gonna. And they were like, oh, maybe it was an inside job because they hit it in such a way that the whole. They're like, no. If they really knew what they were doing, they could have made it come down instantly. Right, so why didn't they make it come down instantly if it was an inside job? Why did they allow thousands of people to escape the building before it could collapse? So wouldn't you want to make it so
They didn't want all the.
they didn't want all the people to die? God damn it, Luke! I didn't think. God damn it.
Who's the person on the inside that wanted this to happen?
Yeah, who wanted? What's it? Who?
Bush.
Okay. God damn it, Luke. God damn it.
That was the only reason he got a second term.
No, yeah, but.
I thought there was billions of dollars the day before.
Yeah. What? Yeah. What
Oh, you're on the team too, Gavin. Fuck,
All
man.
I'm saying is like.
Oh my God. Oh, I just.
$2.5 trillion that went missing the day before.
Oh my God, conspiracy. Oh my God.
Plane hits.
What's your thoughts on if the Earth is flat or not? Where we sitting here?
I don't think the Earth is flat.
Okay.
100% flat.
Oh, yeah. God damn it. Oh.
You want to keep going with this?
No, I don't. I'm running away from this one. I'm running this one.
What other conspiracy theories?
Yeah.
How are the pyramids made?
The moon, right? Like, there's a lot of people that worry about, were we actually on the moon or were we not on the moon? The moon landing, yes, the moon landing. Did that
I
happen?
thought you were going to argue whether the moon was real. There is a conspiracy theory on that.
No, there is, absolutely,
That
right?
the moon is just fake.
Yeah. No, absolutely.
Really made of cheese.
Yeah. Right, but there's, oh my God. But the moon landing, that's a big one. That's a big controversy, right? You ever see that where they, who's the guy that landed on the moon first, was he?
Neil Armstrong.
Neil Armstrong. Yeah, somebody confronted Neil Armstrong.
All in his interviews, he said that he never landed on the moon.
That's he did not, Gavin. He
I
was some
saw
guy.
it on Instagram and I was like,
He didn't say that. There was a guy came up to him a few years ago before he died. He died, right? He died, right? Exactly. A guy came up to him was saying you didn't go on, and he fucking punched him. An old man punched the fucking guy. Yeah. Fuck you, and that's yeah.
Because he was exposing me.
He wasn't, dude. That is so cool that we went to the moon. 1960s technology, but if you believe it. But have you ever driven in a car from the 1960s? It is fucking terrifying. That's the technology that we use to go to the moon, theoretically. Right?
we went to the moon before we put wheels on suitcases.
Yeah.
It was still legal to drink and drive at that.
Yeah, you're right. Right. Still should. Neil.
It still is now.
It's, oh yeah, to a point. But you can't have an open container.
That's when it changed.
Don't, you motherfuckers, dude. Like, God, so I've been around long enough to see, I don't like the drinking and driving thing, because there was one of our students, his name was Cal, and that's what he did. He was in Helena, this is probably 15 years ago, he was in Helena, and he got really drunk at a bar, and then tried to drive to his place in Clancy. And then he was super drunk. And on his drive, something happened, his car broke down. So he left it in the middle of the highway. And he got out and started walking down the highway. And somebody came around the corner who was also drinking and driving and hit the car and died. And fucking Cal went to prison, right? And he went to prison for like 10 years, and he came back and he finished his degree with us and stuff like that. So don't fucking drink and drive. It literally happens. Fucking Neil, don't ever do it. Don't ever do it. It fucking happens, right? It's real. It's real. Okay.
Unlike the moon landing.
Unlike the moon landing. God.
We might need to post a makeup lecture after this.
Yeah, we might have to. This is good. I do. So I have to take a moment to be, because there's an example would be Kyle Boyd, who's going to teach our class in a couple weeks. When he was one of our students, he was like, he always talked about, I'm driving to Missoula, I got to stop and grab some road sodas, is what he called it, right? It's like, God damn it, you can't do it. So I told him to Cal, and now he's like, oh, you're right, I never really thought of it, like it can actually happen to you. It actually can. So now he doesn't do it because he's fucking Columbia Falls, which is just as bad as Billings.
roadies.
Yeah, roadies. Don't do roadies. Don't fucking.
One for the ditch.
You hear these things, but you don't really do it.
No.
Yeah, right. So,
Yeah, not around here.
no. God damn it. Fuck. Oh my God. You guys are. Don't do it. Don't do it, right? I also got a big speech on speed as well. Speeding. Yeah, right? What you gotta do, and I need to make a graph about this, but like, you gotta think of it in terms of how much time does it take me to get someplace versus how fast you're going, right? Because then you wouldn't want to speed so much, right? So I gave my speech to my kids this morning, right? Or this weekend. They just got their license, and he drove to Butte for a bike race, and I was in the passenger seat with him. It was his first time on the interstate. It was fucking terrifying. And so I gave him a big speech.
During his
He got his license. He has his license now. So.
But you didn't let him drive on the interstate
No,
while he had his permit?
no, you don't
practicing?
understand how scary it is. You have this child that you raise that you taught him how to walk, and then you know how they lack certain skills, and then you don't want to like risk your life. We also have a policy that anytime you go over 45 miles an hour, we cannot have all 4 family members in the car at the same time because we don't want to wipe out the whole family at the same time.
You're driving?
No, if I'm driving, it's okay. Yeah. Sorry, when the kids are driving. So we're driving over there, and I gave the talk, and we did the math. If you drive from here, say Butte's 100 miles away, right? If you drive, how far is Butte? Well, just say it. So you're driving to a place 100 miles away. If you drive 80 miles an hour, it takes you an hour and 15 minutes. If you drive 100 miles an hour, it takes you an hour, right? 15 minutes. You've ever ridden, that's a big difference. 80 to 100, like my fucking cars shake a shit ton, right? Like it's a little bit much for your car to go 100, right? Even for 15 minutes. Is it worth that 15 minutes to drive 100 miles an hour and then risk everybody's life there at the same time? Also, right, then you think in terms of energy, the energy that your collision is going to have, right? That term, kinetic energy, is 1/2 mv squared, right? So that's exponentially, your energy is just shooting through the roof. The difference between 80 miles an hour and 100 miles an hour, well, I didn't do the math on that one, that's squaring stuff, that was a lot, but it is an order of magnitude higher when you get into an accident at 100 versus 80, right? So just slow it down and start thinking of things in terms of how long it takes you to get there. Like, so a difference would be 80 to 85 even, right? Now you're looking at even now you're looking at like 4 minutes difference, right? So if you go 85 versus 80 between here and Butte, you're 4 minutes. That's what it's 4 minutes difference, right? Is it worth going 85 and then if for 4 minutes? You're right, and then weaving in and out of traffic and passing semi trucks and stuff like that. It's not, and it gets even exaggerated more. Like when you think of going to Bridger, right? Bridger's only 15 miles away. Like, do you need to drive 80 miles an hour to go 15 miles? Or if I drive 65 and go 15, again, we're looking at 2 to 4 minutes difference. Like, don't fucking do it. Just don't need to do it. Don't 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 do
What
it.
about the fun fact?
If you drive to Seattle,
What if you just get bored driving? You want to speed?
But then you're putting it's not just your life that you're putting at risk, it's everybody's life that you're putting at risk.
Only if you're bad at it.
But if you're mechanical failure or something like that happens, yeah.
no speeding and drinking at the same time.
No.
That's my rule. You can only break. My rule is you can only break one law at a time. It's when you start breaking two. of
I'm
them.
literally sweating, partly because of this, and then partly talking to you sons of bitches. Hopefully you're just being devil's advocates. Hopefully you're not just a bunch of fucking evil people. And I'm just gonna.
Maybe you should see if MVT has that seatbelt like model thing where they put you in a seat and run it down a ramp at like 10 miles an hour.
I'm gonna see what it feels like.
Yeah.
What I always do when I'm driving on a 2-lane road is I'm just when you pass cars, I picture myself hitting that car.